So hello everyone, welcome to the channel. So in this video I'm gonna show you the soil moisture estimation using Sentinel-1 SAR Imagery in Google Earth Engine. So now let's get started. So soil moisture plays a critical role in hydrological and agriculture and climatic process, influencing the water availability, crop yield and ecosystem stability. Accurate soil moisture estimation is essential for effective water resource management, drought monitoring and precision agriculture. The traditional methods of soil moisture measurement using ground-based sensors and in-situ sampling are often limited in spatial coverage and frequency, making the remote sensing a valuable tool for large-scale soil moisture assessment. So among various remote sensing techniques, the synthetic aperture radar provides a reliable means of estimating the soil moisture due to its all-weather capability and sensitive to surface roughness and dielectric properties. So Sentinel-1 is a dual polarization C-band SAR mission from European Space Agency, has proven effective for soil moisture estimation, particularly when using VV polarized backscattered data. A time series analysis is conducted over the selected study region, utilizing Sentinel-1 SAR imagery, both ascending and descending orbit data, to generate the soil moisture indices. The study employs the temporal compositing to create a 10-day average dataset and applies the sigma naught conversions and speckle reduction technique to enhance the data quality and utilize the land cover to mask to exclude the water bodies in urban area to increase the accuracy of this estimation. The soil moisture index is computed based on normalized backscattered value and the results are validated using designated subregion. Additionally, the soil moisture trend are visualized through time series analysis, offering us the seasonal variation of the soil moisture. So this demonstrates an efficient methodology for large-scale soil moisture estimation. So the methodology adopted for soil moisture estimation using Sentinel-1 SAR imagery. So first we're going to define our region of interest, followed by we're going to load our Sentinel-1 SAR data and we're going to filter it based on ascending and descending orbit and to create a 10-day composite image and to convert the SAR backscatter to a power scale and apply the speckle noise reduction technique to enhance the data quality and load the water in urban to mask to remove the unwanted areas. And last, to perform the normalized data to compute the soil moisture index and to visualize and analyze the soil moisture over time. So we're going to export our the soil moisture image to our Google Drive. So now let's get started. So to estimate the soil moisture, so first we have to define our region of interest. So to define a region of interest, navigate to your region of interest and click this option called draw a rectangle. So once you did that, we're going to draw a rectangle over the study region here. And once you did that, we have this variable called geometry. So in that, we're going to click this option called show generated code. And I'm going to copy this latitude and longitude of the study region using Ctrl C in my keyboard. I'm going to copy this and paste this value in this latitude and longitude in the variable study region quartz. Now paste it using Ctrl V in your keyboard. So once you pasted your latitude and longitude in the variable study region quartz, so basically this variable holds the latitude and longitude of the study region. So let me exceed this and turn this off. So once this variable is holding our latitude and longitude of a study region, next we have to convert this variable to a polygon. So to do that, we're going to define a variable study region equals to earthengine.geometry.polygon study region quartz, that is our study region. And to center this layer, we're going to define map.center object study region with the suitable zoom level. So my suitable zoom level is around 11. And last, to add this layer, we're going to define map.add layer study region, that is our study area. And we're going to set the default visualization parameter and we're going to output the layer name as study area. So let us run this code. We're going to click this option called run code, and here you can be able to see in the layers section we have our study area layer. This is our study region. So in the next we're going to define the time range for our analysis. So to define our time range for an analysis, we're going to define a new variable called variable start date equals to earthengine.date. So we're going to specify the time of our analysis, that is 2070, and variable end date we're going to specify the end of our analysis, that is 2024. So next we're going to define another variable called time difference. So basically we are applying this, creating this variable in order to calculate the total number of days between the start day of analysis and to the end day of analysis. So in order to calculate the total number of days between the start of our analysis and the end of our analysis, we are using this variable. We are creating this variable called time difference equals to end date dot difference start date. So the start date, the end date is 2024 and the start date is 2017. So to calculate, and the unit is in day. So to visualize the total number of days between the start and end day, we are using this specific variable time difference. And to visualize the number of days, we're going to define print time difference. And now let us visualize it. I'm going to click run script. And the console section, you can be able to visualize here. We have a total number of days is around 2,556 days between the start and the end of our analysis. So in our next step, we're going to load and process the Sentinel-1 SAR imagery in Earth Engine. So let me explain about this particular data. So Sentinel-1 SAR GRD C-band Synthetic Aperture Radar ground range detected log scaling. So the dataset availability is from 2014 to 2025, and the dataset provider is European Union ESA Copernicus. And this particular dataset can be accessed using this link here, that is earthengine.imagecollection Copernicus S1 GRD. And these are the following band that is available in this dataset here, starting with HH band, that is single co-polarization, horizontal transmit and horizontal receive, and HV is dual band cross polarization, horizontal transmit and vertical receive, and VV, that is single co-polarization, vertical transmit and vertical receive, and last is VH, that is dual band cross polarization, vertical transmit and horizontal receive. And all this band has a resolution, spatial resolution of around 10 meters. So you can able to see from here. So now to load up our Sentinel-1 SAR imagery, we're going to define a variable Sentinel-1 data equals to earthengine.imagecollection Copernicus S1 GRD, and we're going to filter with our start of analysis and end of analysis period. So to do that, we're going to define this function called dot filter date function, start date and end date. So the start date here states the 2017 and the end date here states 2024. And next we have to filter based on our region of interest. So to do that, we're going to define this function called dot filter bound study region. So we're going to filter it based on our region of interest. We are applying this function called dot filter bounds. And in the next step, we're going to filter it based on the type of polarization, that is transmitter receiver polarization. We're going to specifically select the VV. So to select that our transmitter receiver polarization as vertical polarization, we're going to define dot filter earthengine dot filter dot list contains transmitter receiver polarization VV. So let me explain about VV here. So VV polarization, the radar transmits vertically polarized waves, and the receiver also detects the vertically polarized component of the backscattered wave. This means both the transmitted and received signals are vertically polarized. So the basic interpretation example is in an image, area with high VV backscattered appears brighter, indicating the surface that are rough or have a lot of vertical structures. So conversely, the low VV backscattered appears darker and typically indicating a smoother surface or open water. So in the next step, we're going to select the type of instrument mode. So we're going to select IW. So for that, we're going to apply this function dot filter earthengine dot filter dot equal instrument mode is equals to IW. So the IW here represents the interferometric white swath. So interferometric white swath mode is one of the primary operation modes of Sentinel-1 Synthetic Aperture Radar instrument, which is used for a wide range of Earth observation applications. This mode is specifically designed to capture the high resolution imagery over a wide area, making it suitable for an applications such as land monitoring, oceanography and disaster response. So IW mode can capture the data in both single polarization and dual polarization, that is VV plus VH or HH plus HV. The dual polarization capability enhances the ability to differentiate between the different types of land cover and surface conditions. The common use of VV and VH polarization in IW mode allows for more comprehensive analysis of surface features, as it can capture both vertical horizontal scattering information. As the name suggests, the IW mode is optimized for interferometric applications. It enables the generation of interferograms, which are used to measure the surface deformation and topographic changes in the land subsidence with high precision. So now we're going to select the instrument mode to be interferometric white swath. So to do that, we define dot filter earth engine dot filter dot equal instrument mode equals to IW, that is interferometric white swath. And next we're going to select the VV band, that is let me show you that. VV is single copolarization, vertical transmit and vertical receive. We are selecting this particular band, has a resolution of 10 meters. So next let me explain about the orbital property pass here. So orbital property of Sentinel-1 SAR imagery, ascending and descending passes. So Sentinel-1 is the constellation of synthetic aperture radar satellite operated by the European Space Agency, designed for continuous Earth observation. It consists of two satellites, that is Sentinel-1A and Sentinel-1B, that provides a coverage of entire planet with high temporal resolution. These satellites operate in both ascending and descending orbital passes, allowing for the comprehensive monitoring of Earth's surface. Understanding these passes is essential for interpreting the SAR imagery accurately. So ascending pass. An ascending pass occurs when the satellite moves from south to north, passing over the Earth's surface. This generally means that the satellite is moving from a lower latitude to a higher latitude, typically during the local night or early morning hours. So orbital path. During an ascending path, the satellite's orbit takes it from the southern hemisphere to the northern hemisphere. The ground track of the satellite moves from west to east due to the rotation of Earth. And similarly, the descending path. The descending path occurs when the satellite moves from north to south, generally passing over the Earth's surface during the local daytime or afternoon. In this path, the satellite travels from a higher latitude to a lower latitude. So the orbital path is during a descending path, the satellite's orbit moves from northern hemisphere to the southern hemisphere. The satellite travels westward in its orbit while the Earth rotates eastwards beneath it. And the ascending path, this occurs when the satellite moves from south to north. During this path, the satellite captures an image while it is in ascending from a lower to a higher latitude. The local solar time for ascending paths typically falls in late afternoon or evening. And descending path, this occurs when the satellite moves from north to south, and during this path the satellite captures an image while descending from the higher to a lower latitude. The local solar time for descending paths typically falls in early morning. So now to view the details of our orbital property pass, we're going to define print unique orbit passes as an orbit pass. The Sentinel-1 data referring to our Sentinel-1 SAR imagery dot aggregate array orbital property pass. So to visualize the details of orbital pass, we have defined this. So in the console section, you can able to visualize the unique orbit pass. We have both descending and ascending. So we're gonna use both ascending and descending orbit pass. So basically, the Sentinel-1 SAR imagery has a two orbit pass types, that is ascending and descending. So now in the next step, we're going to separate the ascending and descending orbit data. So to do that, we're going to define a variable ascending data equals to Sentinel-1 data dot filter earth engine dot filter dot equals to orbital property pass ascending. And similarly, we're going to define another variable descending data equals to Sentinel-1 data dot filter earth engine dot filter equals to orbital pass property is equals to descending. So now we separate the ascending and descending SAR imagery for our time series analysis. So ascending, which represents the evening pass, and the descending is morning pass. So next, to create a 10 days temporal composite. So in the next step, we're going to create a 10 days temporal composite of SAR imagery. So to do that, we're going to define a variable called date list equals to earth engine dot list dot sequence 0. To create a 10-day temporal composite, we're going to define 0, time difference of unmentioned 10. And next, we're going to create a loop function called dot map function interval, and inside the loop we're going to return earth engine dot date dot from year, month and day, that is 2017 January 1, and dot advance interval in days. So basically we are creating a temporal composite or 10 days temporal composite, and the interval, the units is in days. So it's going to generate a list of dates every 10 days for compositing SAR imagery. So in the next step, we're going to create the composite for ascending image, for ascending orbital pass. So for that, so we're going to create a variable called composite ascending equals to earth engine dot image collection date list dot map function. So we're going to create another loop function. So it's going to iterate over a list of dates, and each date represents a start of 10 days period. And inside the loop, we're going to create another variable called start date equals to earth engine dot date, and inside we're going to mention our date. So this code that converts the current date into in the iteration into earth engine date object. And next variable we're going to mention variable end date equals to the start date dot advance 10 units in days. So to create a 10 days temporal composite, using this advance function. So dot advance 10 represents the 10 days, and the unit is in days. So basically it moves forward 10 days from the start date to define the composite period. So in the next step, we're going to filter the SAR image that falls within the 10 days period, and average the pixel value from all image in 10 days period for reducing noise. So for that, we're going to define a variable composite image equals to ascending date data. So representing which represents this particular variable here, ascending data here. And we're going to filter using this dot filter date, and we're going to mention the start date and end date. Start date is 2017 and the end date is 2024. And to get an average image, we're going to define dot main function. So basically it filters the SAR image that falls within the 10 day period, and it's going to average the pixel value from all images in 10 day period for reducing noise. So in the next step, we're going to check how many bands are available in the composite image, and ensure that at least one valid band is available before storing it. So in order to check that, we're going to define a variable band count equals to composite image, referring to this particular variable, and dot band names. So in order to see then how many bands are available, so we're going to mention band names, the types of band that is available. To check that, we define dot band names function, and to check the size of the bands or the number of bands, for that we're going to define this function dot size function. So this checks how many bands available in the composite image, and which ensures at least one band is available before storing it. And our next step, we have to add some metadata and filter the invalid composite images. So to do that, we're going to define return composite image. So we're going to add some metadata to it. So to add a metadata, we're going to define dot set system time start, comma start date dot millisecond function. So it saves the start time of the composite in millisecond format. And similarly, we're going to set system time end end date dot millisecond function. So it saves the end time of the composite image in millisecond format. And last, to add the metadata property to stores the number of bands in this composite image. So we're going to define dot set band count. So band count refers to this particular variable, and basically this code stores the number of bands in the composite image. And in the next step, we are filtering the composite image, which should have at least one band in it, to perform analysis proceed further in our analysis. So this image might have even have a 0 bands in it. So in order to avoid that, we are applying this specific code here. So for example, let me run the code without this code here. I'm going to run this code here. So from here you can able to visualize the composite ascending. So we have around 256 elements available. I'm going to click this down arrow button. So in the features, we have a list of 256 elements. I'm going to click this arrow. So you can see we have a lot of different around 256 composite images available, and in that we're going to check all this image. So each image has at least one band in it, so you can able to see. And you can able to see in the image 158 it has a 0 band, so it has no bands in it, and compared to 159 it has a 1 band in it, so you can able to see the list has one element. So to avoid the composite image containing no bands, so basically we're gonna keep only images where at least one band is present, so in order to remove the empty composite. So to do that we are applying this code here, that is dot filter earth engine dot filter dot equal band count equals to 1. So it keeps only images where at least one band is present in the composite image, to avoid any empty composites present in our to avoid empty composite images. So for that we are using this code here to filter out the empty composite images. So to visualize the details of this image, I have defined print composite ascending and output the ascending composite. So now let us run this code again. And now in the console section you can able to visualize we have this image collection 251 ascending composite. Now in the features we have around 251 elements. So all this images has at least one band in it, you can able to see that, and we managed to filter out the empty bands in the composite image, you can able to see. So in the next step we're going to perform the similar steps for the descending orbital pass. So for the descending orbital pass we made similar steps. So we defined a variable called composite descending equals to earth engine dot image collection datelist dot map function. So we're going to create a loop function, and the variables inside the loop we're going to create a variable called start date equals to earth engine dot date. So similarly it converts the current date in the iteration into earth engine date object, and for variable end date equals to start date dot advance 10 and the units in days. So it moves forward 10 days from the start date to define the composite period. So to create a 10 days temporal composite image for our analysis. So in the next step we're going to filter the SAR image that falls within the 10 days period, and average the pixel value from all images in 10 days period for reducing noise. And to do that we're going to define a variable composite image equals to the descending data, and we're going to filter based on our start date and end date, and we are applying a mean function to average the pixel value from all images in the 10 days period. And in the next step to see how many bands that is available in the composite image, we are using this function called how many band types and the size of the bands. So for that we are using this dot band names and dot size to see the number of bands that is available in it. So for that we're going to define a variable band count equals to composite image, referring to this particular variable here, and applying dot band names. So to visualize the band names in this composite image and to see the number of bands that is available, we are defined dot size function. So we are using this code specifically to check how many bands available in the composite image and ensure that the result contains at least one valid band before storing it. And to add the metadata properties related to system time start and system time end and band count. So we're gonna use this, we're gonna return the composite image, and in that we're gonna set some set system time start and the start date in millisecond format using millisecond function, and similarly we're gonna set the system end time using the end date dot millisecond. And last we're going to set to check for the number of bands that is available in the composite image, we're going to define dot set band count, and we're going to mention band count here referring to this particular variable, which is going to give us the number of bands that is available in this composite image. And last to filter out any empty composite, we are applying this code dot filter earth engine dot filter dot equal band count equals to 1. If there is no band is available, it's going to remove those composite images. So only we're going to visualize the band, the composite image with at least one band in it. And last to visualize it, we're going to define print composite. We're going to mention it as composite. We're going to mention it as composite descending, the referring to the variable, and we're going to output as descending composite. And now let us run this code again here and let us visualize the result. In the console section, we have this ascending composite. So we have a total of around 173 images available in the descending composite. In the ascending, we have around total of 251 images available. So in the features, so you can able to see all the composite image have at least one band that is available in this composite image. You can able to see here. So in the next step, we're going to convert the SAR data from decibels to a linear scale. So and apply the speckle filter. So to do that, we're going to define a variable called process SAR equals to the function image. We're going to create another loop function. So inside the loop, we're going to create a variable sigma naught equals to earth engine dot image 10 dot power image dot divide 10, and we're going to rename as sigma. Basically, this code converts the decibels to a linear scale. So in order to perform our analysis, we have to convert from decibels to a linear scale. So for that, we are applying this code to convert to a linear scale in order to perform our analysis. Generally, this our data is in decibels, so we have to convert to a linear scale to perform our analysis. So for that, we are applying this code, and next we're going to define another variable called speckle reduced. So we're going to apply the speckle filter in order to remove the speckle noise in the SAR imagery. So for that, we're going to define a variable called speckle reduced equal to sigma naught equals to sigma naught dot focal mean 30 in square meters. So units, we have defined the units are in meters, and we have defined this in square. So once we applied the speckle filter, and last we're gonna return the speckle reduced dot copy properties. So we're gonna copy the metadata property of this image to our speckle reduced image. So for that, we are defining return speckle reduced dot copy properties image dot property function. And last, to apply those the linear scale and the speckle filter to the existing composite ascending image and to the composite descending image, we are defining another variable called sigma ascending equals to composite ascending dot map process SAR. So we are applying the SAR pre-processing to the composite ascending and to composite descending using the variable sigma ascending and say a variable sigma descending. And in our next step, we're going to load and process the land cover maps. So now in the next step, we're gonna compute our soil moisture index. So to do that, first let me explain, show you the formula. So to compute the soil moisture using SAR Imagery, so the SAR soil moisture index is computed using this normalized backscattered value. So the formula is represented as SMI equals to sigma minus there is sigma naught minus sigma naught mini divided by sigma naught max minus sigma naught mini. So you can able to see the sigma naught represents the SAR backscattered in the power scale, and the sigma naught mini is the minimum SAR backscattered value, and sigma naught max is the maximum SAR backscattered value. So now to compute this soil moisture estimate, let me get back to Earth Engine. So to compute that, first we need our minimum sigma, say we require the sigma naught minimum and sigma naught maximum. So to compute the minimum backscattered value and the maximum backscattered value, first to compute the minimum backscattered value, we're going to define a variable minimum ascending equals to the sigma ascending dot minimum mini function. So to compute the soil moisture index for the ascending orbital pass, so for that we are defining a variable minimum ascending is equals to sigma ascending dot minimum function to acquire the minimum backscattered value, and similarly to acquire the maximum backscattered value, we define another variable maximum ascending equals to the sigma ascending dot maximum function. So it computes the maximum backscattered value in the dataset. So next we're going to create a loop function to estimate the soil moisture index. So for that we're going to define a variable soil moisture ascending equals to sigma ascending dot map function image. So it's going to loop through each image and it's going to apply the soil moisture index formula. So to apply the formula, we're going to define another variable moisture index equals to image dot subtract minimum ascending dot divide maximum ascending dot subtract minimum ascending. Basically we are applying this particular formula here. We are applying this particular formula, the sigma naught minus sigma naught minimum divided by sigma naught maximum minus sigma naught minimum. So let me get back to Earth Engine. So in the next step, we're going to convert the image timestamp into a formatted string in year, month and days. So like year, month and days. So to do that, we're going to define a variable date formatted equals to image dot date function. So we are applying first the date function and we're going to format in this way, like year, month and day. And the last we're going to return the moisture index and to remove the water pixels and urban pixels. So we are applying dot multiply water mask and dot multiply urban mask. So basically it's going to remove the water and urban pixels in the image, and we're going to rename as the soil moisture ASC, that is ascending soil moisture ascending orbital pass. And to copy the time metadata properties to the image, we can define dot copy properties image system time start. And to set a date property for our time series analysis, we're going to mention dot set date Earth Engine dot string date formatted, which is referring to this particular variable. So in the last step, in the next step, we're going to add this layer to Earth Engine. So to do that, we're going to define map.add layer soil moisture ascending dot filter. We're going to apply the filter function from 2020 to 2021 and dot two bands to combine multiple images into a single banded image. We are using this two band function, and to clip it based on a region of interest, we are applying dot clip study region with the default visualization parameter, and we're going to output the layer name as soil moisture ascending. So in the next step, we're going to define a sub-region for our time series analysis for the soil moisture index within this study area. We're going to define another sub-region to visualize the soil moisture for this sub-region within this study region. So to do that, we're going to apply the similar steps here. So first let me navigate this option here. Going to delete this. And now we're going to create a sub-region. To do that, we're going to click this option called draw a rectangle. So I'm going to create my sub-region within the study area. For example, I'm going to create a polygon like this. So to convert to a satellite mode, so I'm going to analyze the soil moisture for this specific subregion within the study area. So once you created a polygon, let me navigate to this option. I'm going to copy this latitude and longitude of the subregion, and I'm going to paste it inside this variable. I'm going to copy this, and I'm going to paste it in the subregion variable. So this is my subregion variable. I'm going to paste this, the latitude and longitude, in this variable here. So once you did that, so we have managed to create a subregion for our time series analysis for the soil moisture for this subregion. Let me turn this off. So to convert this subregion to a polygon, we're going to define another variable called validation area equals to earthengine.geometry.polygon, and referring to validation area chords, which with this variable contains the latitude and longitude of the study region. And to add this layer, we're going to define map.addLayer validation area with the default visualization parameter, and we're going to output as validation area. So once we have converted the subregion into a polygon, next we're going to create a time series analysis for our soil moisture index value. So to create time series chart, we're going to define print ui.chart.image.series, and image collection we're going to mention the soil moisture ascending. So we're going to create a soil moisture index for our ascending orbital pass. So we have mentioned the image collection as the soil moisture ascending, and the region is our validation area, that is subregion. And the reducer, we are applying the reducer. So in order to compute the mean value for our time series analysis, and the scale value we're going to mention as 30 here. So we can also mention the 10 meter as your scale value. So but to increase the speed of the computation, we have mentioned as 30 meters. And X property, which represents the system times start property, and you can set the following options to your chart here using dot set options: title, soil moisture time series for ascending orbit. So in the h-axis, I'm going to define the title as year, and we're going to format in year, and the grid line, so we're going to mention as the count to be 8. And v-axis, the title, I'm going to mention the soil moisture index. The value ranges from 0 to 1, with a minimum starting from 0 and to a maximum value of 1. The grid lines, so like this you can set different options to your time series chart. And the next step, we're going to visualize the result. I'm going to click this option called run, and let us visualize the result here. So this is the you're going to visualize the first chart here. So you can able to see this is a soil moisture time series ascending orbit. So this axis represents the soil moisture index, and this axis represents the year starting from 2017 to 2024. So you can able to see the value ranges from 0 to 1. So the value closer to 0, which indicates the dry condition, and the value closer to 1, which indicates the wet condition. And this time series chart for our ascending orbit. And similarly, we're going to create a time series chart for the descending orbit too. So to compute, first we have to compute the soil moisture index for the descending orbit. So for that, we know the formula is, this is the formula. So sigma naught minus sigma naught mini divided by sigma naught maximum minus sigma naught mini. So to compute this, first we have to identify the minimum and maximum value. So we define a variable minimum descending equals to sigma descending dot minimum function to acquire the minimum descending value, and to acquire the maximum value, we define variable maximum descending equals to sigma descending dot max function. And we have to create a loop function. So in order to compute the soil moisture index, so for that we're going to define a variable soil moisture descending equals to sigma descending dot map function image, and we're going to create a loop. Inside we're going to define another variable moisture index equals to image dot subtract minimum descending dot divide maximum descending subtract minimum descending. Basically we are applying this formula. So this is the formula we are applying in it. So we have mentioned this formula here. And inside the loop we're going to create another variable called date formatted equals to image dot date function dot format in the year, month and days. So it's going to convert the image timestamp into the formatted string as a year, month and day. And we're going to return the moisture index, and we're going to multiply the water mask, and we're going to multiply with the urban mask to remove the water and urban pixels. and we're going to rename as soil moisture descending. And to copy the metadata properties to this image, we're going to apply dot copy property image system time start. We're going to copy the metadata property of the system's time start to this image. So for that we are applying this function dot copy properties. And last, to set a date property for our time series analysis, we're going to mention dot set date earth engine string dated date formatted. So it's going to set the date property for our image. And last, to add this layer, we're going to define map.add layer soil moisture descending. We're going to filter it based on this particular year from 20 to add this as an image, to filter based on the 2020 to 2021, and to combine the multiple images into a single image, we are using this function called dot two bands, and we're going to clip it based on our region of interest. We are using this dot clip function. We have mentioned a study region, that is this particular study region, this entire study region, with the default visualization parameter, and we're going to output as a soil moisture descending. So in the next step, we're going to generate the time series chart for our descending orbital pass, that is our soil moisture time series chart for our descending orbital pass. So to do that, we're going to define print ui.chart.image.series, and image collection we're going to mention as soil moisture descending, and region is our validation area, that is this subregion. And reducer we are applying to acquire mean value, we are applying the statistical function earth engine dot reducer dot mean function, and we have mentioned the scale as 30 meter to increase the speed of computation, and the x property system time start, and we can set the additional options to this time chart by using this dot set options. We're going to mention the title as soil moisture time series descending orbit, and the h-axis we can define title as year, and the formatting as in year, and grid lines we're going to mention is count 8, and the v-axis the title is soil moisture index from 0 to 1. We set a minimum value of 0 and a maximum value of 1, and you can set a variety of different options things to this times chart. For example, series I have mentioned as a color as a orange red line, and the line width and the point size you can also do that, and the trend lines you can apply the trend lines, you can apply the color and the line width and the opacity of those then trend lines. So let us visualize this chart here, the descending soil moisture for descending orbital pass. So you can able to see here the graph soil moisture time series. So the value ranges from 0 to 1, so from 2070 to 2024, so the value ranges from 0 to 1, you can able to see. So we managed to create a time series chart for both ascending and descending orbital pass for our soil moisture index for the study region, so the specific subregion. So now let us visualize the soil moisture for ascending orbital pass for this entire study region here. So let's go to load the image. Let me turn on both these layers, the soil moisture ascending and descending. So now we are visualizing the moisture index for descending orbital pass satellite image. You can able to see here. So I'm going to navigate this option here. I'm going to click this, and in this I'm going to click as this one band grayscale, and in the custom section I'm going to apply stretch 90%, and once it get loaded I'm going to click apply. So you can able to see the value ranges from 0.08 to 0.78. I'm going to click apply. So image is getting loaded here. So you can able to see from this image here all the white spot in the image which indicates the high soil moisture values, and all the dark values which indicates the low soil moisture values. So you can able to see in this area here which has a higher value, so you can able to see the white patches which indicates the high soil moisture value. I'm gonna close this and turn to a satellite mode, and gonna apply some transparency. I'm gonna adjust the transparency here. For example, this particular area has a white patches which indicates the high moisture values. I'm gonna turn this off. You can able to visualize this from this image. And similarly towards this part of the region, so here we have you can able to observe it has a high white patches which indicates the higher moisture values. So you're going to zoom into this part of the study region. So you can able to see from this image here So this particular image has a higher the image getting loaded here. Let's wait for some time. So you can able to see from this image here. So this particular area has a high moisture values. So it's the whiter patches which indicates the high moisture values, and the darker patches which indicates the low moisture values. And all these values which indicates the masked values. For example, the urban areas and water bodies are completely masked out, and the white patches will indicate the high moisture value. And similarly, let us visualize for soil moisture value for ascending orbital pass image. I'm gonna turn this on, I'm gonna turn this off. So now the image has loaded. So in the soil moisture for ascending orbital pass, I'm gonna click this option, and further I'm gonna select single band grayscale, and you can select the different images for in the different time period. So we're gonna select for this particular one, and I'm gonna adjust the transparency, the stretch of this stretch type. I'm gonna select to be stretch 90%. So now the value ranges from 0.1 to 0.9. So I'm gonna click apply, and let us visualize the result here. So the image is getting loaded here. So you can able to see from this image all the white patches which indicates high moisture values, and you can able to see in this part of this image has a very high moisture value compared to this part of the region which has lower moisture values. So because let me adjust the transparency of this layer. So you can able to see from this image, I'm going to adjust the transparency. So this portion of the study region which is has a lot of vegetation, and this is the exposed land here. So this exposed land, we can able to estimate the soil moisture of this area. So you can able to see now the white patches which indicates the higher moisture values. So you can able to see, and all the darker areas which indicates the urban and the water bodies, we have masked it out. You can able to see all this white which indicates good moisture values, and the value which ranges from 0.1 to 0.9. The value ranges from 0.1 to 0.9, and based on the interpretation value for the soil moisture index. So if the soil moisture index value ranges from a value of 0, which indicates the low moisture soil moisture, typically corresponding to dry, sandy or non-vegetated areas, and if the value ranges from 0.1 to 0.4, it is moderately dry soil. It represents a soil with a low moisture and often found in arid or semi-arid regions. And the value ranges from 0.4 to 0.6, so it indicates the moderate soil moisture level, and 0.6 to 0.9, which corresponds to a soil with high moisture content, so the found in the regions with the recent rainfalls or irrigated fields. And the value of 1 represents the waterlogged or near saturated soil, often observed in the wetland, flood zones, or after heavy rainfall. So in the last part of the step, we have to export this image to a Google Drive. So to do that, we're going to define export processed to export process soil moisture data to a drive. We're going to define export.image to drive, image soil moisture descending. So we're going to filter 2020 to 2021 and 2 bands. To compile all the bands together, we are using this 2-band function, and we're going to clip it based on our study region. And the description is soil moisture descending 2020 2021, and the spatial resolution I'm going to set to 10 meters, because the Sentinel-1 SAR Imagery has a spatial resolution of 10 meters. And the region I'm going to define the study region, and the coordinate reference system, and the folder, and the max pixel value. So once you did that, we're going to run this script here, and it's going to run the code. And in the task section, you can able to let me navigate to the task section here. I'm going to click this option task, and here you can able to visualize we have this unsubmitted task called soil moisture descending 2020-2021. So I'm going to click this option called run to export this image to our Google Drive. So then a window pop up saying initiate image export. So the task is soil moisture descending 2020 to 2021, the coordinate reference system, scale, and we can export to our drive, and the file format is in GeoTIFF. So we're going to click run to export this image to our Google Drive. So now let us take a look at the application part of this particular study. So the applications, the crop health monitoring, water resource optimization and yield prediction. So the farmers can assess the soil moisture variation to optimize the irrigation schedules, ensuring the crop receives an adequate water while preventing the overwatering. By identifying the areas with the sufficient soil moisture, the water can be efficiently allocated to the drought prone regions and improving the agricultural sustainability. And the soil moisture data can be integrated with crop model to predict the yield and optimize the fertilizer applications. So early warning system and water scarcity management and impact assessment. So the continuous monitoring of soil moisture helps detect the drought condition at early stage, enabling a proactive mitigation strategies. Governments and organizations can use this data to implement the water conservation policies and allocate resources efficiently in water stressed region. And historical soil moisture data can be analyzed to understand the severity and the frequency of the drought, aiding in climate adaptation policies. And last is the pre-flood soil saturation analysis and landslide risk assessment and disaster recovery planning. So monitoring soil moisture level helps in understanding the soil saturation before extreme rainfall events and aiding in flood forecasting. So high soil moisture level can increase the risk of landslide, making this data useful for hazard mitigation planning in mountainous region. And after flood, the soil moisture data can help assess the waterlogging and plan for agricultural recovery and infrastructure rehabilitation. So now let me get back to Earth Engine. So in this video I have shown you how to estimate the soil moisture using Sentinel-1 SAR imagery in Google Earth Engine, and the link for this code will be given in the description of this video. So thanks for watching, and make sure that you subscribe to our channel and give us a like.